So, this sometimes you have symmetric circuits, that is the same circuit that is copied over and connected in some way. Okay. So, let me take a network N and it can have anything inside, okay, and it has a number of terminals. I show, let us say 1, 2, 3, then maybe it is even connected to ground, meaning the reference node of the circuit, whatever you pick that to be, okay. And then the total circuit is actually a mirror, this and the mirror image of that, okay. There may be any number of other terminals, okay. So, this is a general representation, any of these may or may not be present, okay. So, this may not be connected to ground here and so on, that is possible. But the point is, it is the same network N. Now, if I apply V and V here, okay, that is I apply exactly the same excitation to the two sides. Again, there may not be just one source, there could be multiple sources, like for instance, there could be some other place where you connect a current source, and here also you connect it in the same direction, that is the idea, okay. Now, what can you say about the voltages and currents in this? Currents? Okay, why? Yeah, actually I think it is kind of obvious from symmetry that the currents here will be 0, right? Okay. And if you name the nodes in this in a certain way, and in the same way in the two cases, if you have some node voltages here, you will have exactly the same node voltages there, okay. What kind of circuit do you need for this to happen? I mean, is there any restriction on the network N? Resistive? What kind of circuits for what kind of circuits will this work? Linear circuits. Linear circuits it will work, but actually do you need linearity here? Anything can be there, okay, as long as they are exactly identical. So, this one, it does not matter whether it is linear or non-linear. In fact, later if you do analog circuits, you will see that there are some non-linear circuits where this condition is a pretty common condition, and then you will use that to evaluate the conditions quite easily, okay. Essentially, you can think of it as, let us say you have all these nodes here, okay. So, you fold the circuit on top of each other, so that the corresponding nodes on this side and that side connect. They are at the same voltage, nothing will happen. Basically, you are analyzing half the circuit, okay. So, that is the idea. When you are exploiting symmetry, essentially you end up somehow analyzing half the circuit, that is the advantage. Yeah, it is, all the branch currents will be double, right, because you have two resistors in parallel and so on. So, oh, it will, right, because if the sources are not identical, the two solutions would not be the same. So, an easier way to think about this is, you start with the circuits disconnected, okay. So, these two are not connected to each other, okay. So, now if you connect identical, they are then identical networks and you have identical excitations. So, the voltages here and there will be the same, okay. Then you can go ahead and connect any node to its corresponding node, nothing will change, okay. So, I could connect these two. Then I will go backwards and say, if you started off with a circuit like this, which consisted of slapping together two identical networks which are connected at some nodes, not every node, you can still go back to the original case, okay. Yeah, it does not matter if let us say this is V1 I1, this is V2 I2. If these two are different, the excitations are different, the solutions in this and solution in that will be different. The circuit is the same, but the voltages and currents will be different. So, if you take that node and connect here, some current has to flow there and something will change. Yeah. Yeah, that we can do, but now I am looking at even analyzing only half the circuit, right? Yeah. No, you can't connect the two together because the two, I mean, you start off from a case where they are disconnected. If the voltages here and there are different, you can't connect them, right? Okay. So, this is known as either even mode or common mode. I think in some other context also I mentioned in superposition that you could decompose the sources as not as one source at a time, but maybe the average of the sources and the difference between the sources. This is where it comes from. In this type of context, it is quite useful. Okay. So, in this case, even mode or common mode excitation, the two sides have okay. So, essentially the advantage that you get, the so called advantage is that you analyze only half the circuit. Okay. In fact, if you open circuit this stuff is called the common mode half circuit. Okay. You do not have to worry about these terminologies now, but you assume that you have an even mode excitation, that is you have a network which is composed of two identical networks connected together at some nodes. Then you have some excitation. If you have exactly the same excitation on either side, you can simply cut off one half of the circuit and analyze that alone, you will get the solution. The solution in the other one will be the same as this. Okay. And actually this does not depend on linearity, right, because all I said was if you have two networks, two identical networks with identical excitation, they will have the same solution, that is, that does not need linearity, right. Then you can connect them together whether they are linear or not. Is this okay? And you can have minus V1 minus I1, okay, that is anti-symmetric excitation. These two are still the same network. So, again you have two identical networks and the corresponding nodes in the identical networks are connected together. Not every corresponding node, but maybe a subset of them. Okay. In this case I have shown two nodes which are connected to each other. Okay. But the excitations are antisymmetric, that is if you have V and I on this side, you have minus V and minus I on the other side. So, what can you say in this case? Is there some simplification that you can do? Huh? What's that? Yeah, the nodes which are connected to each other, what about them? What is that? They will be at 0 volts, that is the contention. Few of you are saying that these voltages will be 0, is this correct? How would you prove this? Yeah, but we have to also show that it is Vk and minus Vk, right? So, here what you can do is first take yeah So, first of all you take this case, okay. You have excitation only on one side, right, and 0 on the other side. There will be some solution. That is the solution, right, Vk Ik in this part and let us say Vk prime Ik prime in this part. They will not be the same as each other in this case, the excitation is not symmetric. And then you have 0 here and I1 V1 there. What will be the circuit the solutions? Because they are identical circuit, it is symmetrical, it will be Vk Ik on the right side and Vk hat Ik hat on the left side. And then what? You have to take the negative of this. If this is minus I1 minus V1, then this red stuff will become minus Vk Ik and here it becomes minus Vk hat Ik hat. Okay. Huh? What is that? Current? Current stays the same? Minus, oh yeah, minus Vk hat minus Ik hat, yeah. Okay. So, like I said, these are the common nodes. They would have some solution in this case and the negative of that solution in the other case, and they will superpose to 0. Is this okay? Yeah, no, that's correct. For the same nodes, it has to be the negative of that. Yeah. So, what kind of circuits will this work for? What did we use in all these steps? Huh? So, you just tell me what it works for, okay. Linear circuits, okay. This one is applicable only to linear circuits. It does not matter if it has dependent sources as long as it is linear. So, if you have linear circuits, the linear symmetric circuit with antisymmetric excitation, then the nodes on the center line is basically the axis of symmetry, they will be 0, okay. Then also you can analyze only half the circuit, you can just take one half, connect these things to ground and analyze that, okay. Now, whether to do this or not again depends on the structure of the circuit and so on, right. I mean structure of the circuit and also the context in which you are evaluating it. If you had arbitrary voltages, you had to analyze a circuit of twice the size, okay. So, now we are analyzing half of the circuit twice, okay. So, but this may be functionally significant in some cases, just like I think I gave the analogy earlier of forces and so on. If you have unequal forces, maybe you can superpose them to equal and identically directed forces, and the other one oppositely directed forces, which only creates a torque and so on. So, functionally sometimes this antisymmetric excitation and symmetric excitation have some physical meaning. So, then these things make sense, okay. Any questions? The last. So, if minus V1 and minus I1, let me remove all of this. So, let us say I have V1 I1 and 0 0. This will be some V2 and this will be at some V3, right. Then if I have 0 on this side and I1 and V1 on the other side, what will these be? It will be again V2 and V3, that is all, right. And if I have minus I1 and minus V1, this will become, if the circuit is linear, this will become minus V2 and minus V3, okay. Now, we are looking at a case with V1 I1 and minus V1 minus I1. So, we have to superpose this and that and this and that. Okay. So, it becomes 0. Is it okay? Yeah. No, when you have antisymmetric excitation, currents will flow. Yeah. I mean, just think of a single resistor, right? If you have V and minus V, current will for sure flow. If you have V and V, it will not flow. Okay. The point is, if you have V and minus V, you can split this resistor into two parts, equal parts, and the center will be at 0. So, you could analyze only one resistor of R by 2 instead of two resistors. Is it okay? So, this is also called even mode or common mode. Then you have the same circuit solution in the two halves. Okay. So, you analyze only half the circuit. I mean, basically, you can think of removing the other half or folding over one half on top of the other. They are the same thing. Okay. And this doesn't need linearity. This can be done even for nonlinear circuits. We haven't analyzed nonlinear circuits so far, but this method can be used. Any questions here? You have to find out by circuit analysis. There will be some currents. No, I mean, if the circuit is like this is actually not connected to ground, right? For analysis, you could connect this to ground and analyze it. In that only analysis alone, it will flow to ground. But in reality, if you connect this to ground, the current will be flowing this way and the same current will be flowing there. No current will flow into ground. Okay. There will be some current flowing here. Exactly what current it is depends on the circuit. And similarly, if you have symmetric circuit with antisymmetric excitation, then we'll write nodes along the axis of or nodes on the axis of symmetry. Are at 0 volts. Okay. I think you know what this means. Now, in a case like this, where is the line of symmetry? It is not visible. You have a resistor connected between these two. If you have such cases, you have to connect it, I mean, you have to convert it into two identical ones in series of half the value and then form the central node. Okay. So, this R is also on the axis of symmetry. You can connect, you can imagine that it's 2R in parallel and then pull to the two sides, so that the two halves are separate. Okay. If you want to separate out the halves, that is what you have to do. Okay. So, you again analyze only half the circuit. And in in this case, the common nodes between the two halves you have to ground them. Okay. And once you obtain the solution to this, the solution in the first half will be the same, the solution in the other half will be the negative, right. When I say solution, I mean all the branch voltages and currents. Is this okay? And this of course does require linearity. Okay. So, when you have a symmetric network, that is the same network connected at some corresponding nodes, then you can either analyze the full circuit with whatever inputs you have, or alternatively you could decompose that into the even mode circuit and the odd mode circuit. That is the circuit that the effective circuit that results when you have the same excitation on the two sides, symmetric excitation, or when you have antisymmetric excitation. Okay. So, you will have to analyze half of the circuit twice. So, the net labor may look the same, but like I said, functionally it will have some significance in many cases. Okay. So, you may want something to happen in the even mode, something else to happen in the odd mode, and so on. Any questions about this? And probably that is essentially what you used here as well.